Hey everyone, hello, good afternoon, and happy Friday to everyone. So I think this is it. We'll just finish the last pages of these notes, and that is all I have for class today. And then we'll also end it with some final due dates, right? But before we do housewarming, we kind of abruptly left off here on this problem, so let's just finish it off. Today is 4/23, April 23rd, 2021. And, we kind of stopped right dead in center in the middle of this problem, so I'd like to finish this. All right, so it's being asked, this problem is to calculate delta G naught. Okay, want to bring your attention to that naught symbol. Okay, that means standard state for this reaction. And the reaction, obviously, at standard state is going to be at 25 degrees C. So here's the reaction. The first thing we did was we deconvoluted it. You know what deconvolute means? We kind of split this. Okay, we split this reaction into its component parts. This is, after all, an oxidation-reduction reaction, otherwise known as a redox reaction. So we split this oxidation-reduction reaction into its parts, okay, splitting this into the cathode part. So just want to remind everyone, in a cathode, you gain electrons. Okay, you gain. In this specific example, we are gaining 3 electrons, and cathode is the site for reduction. A lot of students get these confused, so I recommend you memorize red cat eats and ox. And if you memorize that, you'll recognize reduction occurs at the cathode while the anode oxidation occurs. So we split this into the cathode component, which is reduction, and the anode component, which is oxidation. Another thing here is that in oxidation you lose electrons. Here in this specific example, we lose 2 electrons. So the anode is the site of oxidation. Okay. A lot of students confuse these two or flip them. Okay. Reduction is a cathode, occurs at the cathode, you're gaining electrons. So the electrons are on the reactant side. This is important to know. The electrons are on the reactant side for a reduction reaction. And free electrons in an oxidation half reaction are lost, so they're in the product side. Okay, they are released product side. That's also important. Okay, the next important thing as we go over this problem, we split this apart. We get our voltages from our table. So make sure you have this table with you for the exam. I think I have it linked up somewhere in Canvas, so check it out. It's called the Standard Reduction Potential Table. We get the voltages and we cancel out the electrons. Okay, to cancel out the electrons, we multiply the top half reaction. Okay, notice the word here, half reaction. We multiply that by 2, and we multiply the bottom half reaction. Okay, again, notice the word half reaction by 3. So doing that, we will cancel out our 6 electrons. This is a 6 electron transfer reaction. So N equals 6. Which is the number of electrons that are being transferred in this oxidation-reduction reaction. All right, so we add the 2 reactions, canceling out our electrons. We add the voltages. The positive sign tells us that this is, thumbs up. It will favor the products. So we got E cell, but the problem is asking us for, what is it asking for? It's asking us for delta G naught. So here's the equation that we will use for delta G naught. Where did I get this equation? Okay, I got this equation from this little triangle. Okay, sort of relates everything: electrochemistry, thermodynamics, and equilibrium. Okay, so pick the equation that fits you. And for me, this is the equation that will get us delta G naught. Okay, so minus n, that would mean minus 6. Now F is a constant, so I will give you that. It's 96,500 joules per volt mole. Okay, I believe that's what it is. And E cell is positive 0.71 volts. Okay, volts. Okay. So the volts and the volts cancel, and we just put these numbers in. Our final answer is going to be in joules per mole. -6. Okay, let's do this on our calculator really quickly here. -6 times 96,500. This is called the Faraday constant, if you remember. And times the 0.71, which we got from here. And that's a big number, -411,090. Okay, let's divide it by 1,000. Minus 411 kilojoules per mole. Okay. And that should be our answer for the delta G naught. Delta G naught, standard state. All right, the minus sign for delta G, the positive sign for E cell, tell us that this is a reaction favoring the product side. That this is a reaction favoring the product side. A minus delta G, that's called an exergonic reaction. Exergonic. That is a reaction that releases energy, releases useful energy. Not talking about heat. We're talking about energy that could be used to do what we call work. Okay, work. In terms of, I don't know, lighting a light bulb or making a reaction go in the cell. Okay, that's energy, and that's energy that can be capitalized. And that's what Gibbs free energy is. That's what free energy is, and the negative sign tells you it's exergonic. So this is how we will do that problem. I want to introduce you guys to a new equation here. This is called the Nernst Equation. There's two forms. There is a natural log form, or there's a log form. So I'll give you one or the other, okay, for the exam. So these will be given. So what exactly is this Nernst equation? Okay, let me turn off the lights. The Nernst equation is for non-standard state conditions. So you're going to use this equation if you're not, N-O-T, not at standard state. If you're not at standard state. So what is standard state? It's 25 degrees C temperature. It's, if you're talking about gases, 1 atmosphere of pressure. And for a solution, you're not at 1 mole. Molar over liter. Okay, remember, big M means mole over liter. Okay, so you're not any of these conditions, and we call that standard state. If you're not at standard state, you will use these equations for conditions other than standard state. Once again, we have the natural log form and then the log form. I'll give you these. Okay, I'll give you these on the exam. You just have to know how to use it. And also, you need to know what the Nernst equation is for. Okay, it's for, you have to identify, okay, when will I use this equation? Okay? Again, you will use this equation if you're not at standard state. A lot of reactions don't occur at standard state, right? A lot of reactions, for example, in our body don't occur under these ideal conditions. So here we'll use the Nernst equation. So let's go ahead and use that here. Let's do this example problem together. Okay, will the following reaction occur spontaneously at 25 degrees given that Fe plus 2 equals 0.60 and cadmium plus 2 equals 0.010? By the way, let me move back upwards here. I apologize to everyone. Want to bring your attention here to Q. Okay, Q. We use Q and compare it to K. Okay, so Q is calculated and compared to K, which is the K you look up in your textbook. Okay, K being the equilibrium constant. And it goes like this. We want to put Q first. We're going to put Q first. And one scenario is if Q is greater than K, bless you. Okay. If Q is greater than K, the alligator jaws point towards the reactant side. So this is reactants are favored in this equilibrium reaction. It has more reactants than products. If Q is equal to K, then it's not reactants are favored and not the products are favored. So none are favored. It's kind of like 50-50. Okay, equal. And then finally, if Q is less than K, remember we have to put Q first in this alligator rule. The alligator jaws are pointing towards this way, the right, and the right means that the equilibrium favors more of the products. Okay, favors more of the products. Products favored. So that Q goes into the Nernst equation. And also what else I'd like to bring your attention here is this E at standard state. Okay, so you need to calculate E at standard state like we did in the previous couple of problems to get the E under non-standard state conditions. Okay. All right, let's go back here and do some examples, and hopefully this will make more sense. You can automatically tell that we don't have concentrations that are 1 molar, and because of that, we're going to have to use the Nernst equation. Here's the equation that they gave us. The first thing we recognize is that CD, which is cadmium, goes to CD plus 2. So let's write down this half reaction. Okay, how many electrons and where to balance this? 2 electrons on the right. Everyone see that? Okay, so plus 2 and minus 2 gives us 0. Let's look up the voltage for that. By the way, this is an oxidation reaction. Cadmium. Where are you, cadmium? Here you go. You found it first. And let's flip it. All right, everyone see we need to flip this. It will be 0.4, right? So is this the anode or cathode? You lost 2 electrons. Anode. Okay. And then I'll highlight this in red. We have Fe plus 2 aqueous going to Fe solid. Okay, how many electrons and where? 2 on the reactant side. This is a reduction half reaction. Let's see the voltage here. Literally right under it. Okay, so the diagonal rule tells us that cadmium, this is a review of the diagonal rule. The diagonal rule will tell us, if you remember, that cadmium will cause everything below it to flip. Flip, flip, flip. So cadmium can cause iron solid to go to iron plus 2, minus 0.40 plus, because it flips it, everything below it flips it, so you have a positive voltage. Okay, so that's the application of the diagonal rule. Pick any of these reactions, half reactions. Anything below it becomes flipped, you get a positive voltage. Anything below it. What's the voltage on this? Minus 0.44. We leave it as is. Minus 0.4. Okay, we're going to call this the cathode, which is the site of reduction. Okay, we don't need to multiply anything because the two electrons cancel. We have CD solid plus Fe plus 2 aqueous goes to Fe solid plus CD plus 2 aqueous. Okay, it doesn't matter what order you put it in. And look, we just got the same old reaction, but what's interesting here is that we have here a, what's 0.4 minus 0.44? Minus 0.04 voltage. Okay, so here it's a reaction that does not occur. Okay, so cadmium can oxidize iron sulfur. Cadmium can oxidize iron to iron plus 2. Okay, but iron solid cannot oxidize. Is that right? Cannot oxidize cadmium plus 2 to cadmium solid to cadmium plus 2. Okay. Cadmium solid to cadmium plus 2 cannot occur. The opposite can occur. All right, so this we're going to call E cell. Let's figure out Q here. Q is products over reactants. I'm not going to add iron because it's a solid. So it's going to be concentration of CD plus 2. That's called cadmium, divided by Fe plus 2, which is an aqueous solution. All right, cadmium plus 2. Everyone see the concentration? It is 0.010. And the concentration of iron plus 2, let's look that up, 0.60. Okay, so 0.01 divided by 0.6. What is that, 0.166? 0.0166, okay. 0.0167. All right, so that's Q. Let's plug in our equation. I'll use this one, though it doesn't matter which one you'll use. But, on the exam, if I give you this one, make sure you use this one, okay? By the way, what is N here? Correct. But what is the number? 2. Okay, 2. Okay, that's what. Both are correct, but for this particular reaction, N is 2. This is a 2 electron transfer reaction. All right, let's do this. E cell is equal to E cell at standard state minus, I'm going to use this guy here, 0.0257 volts divided by N. Okay, you guys correctly stated that N is 2 times 0.0167. Okay. Yes. Okay. By the way, E cell is minus 0.04, right? Non-spontaneous. Minus 0.0257 divided by 2 times 0.067, which is Q. All right, how will we do this on our calculator? Just be careful, because this is where mistakes can happen. I'll be the first one. I can make a mistake too. So 0.0167 times, I got to be careful here, 0.0257. Okay, I'm going to take that divided by 2. Okay, I'm going to make that minus. Everyone see that? Minus. So minus. Okay, minus, plus, okay, this is tricky, plus, I'm going to put a parenthesis here. Well, you can do it many ways, but plus a minus, this is not, there's more than one way to do this. Plus a minus 0.04. Okay, everyone see that? You can do it your way, whichever way you like it. Same thing, minus 0.040 volts. Okay, is that what you got? Oh, you are right. We do have to do the ln.
We all forgot about it.
Oh, I.
And I also got 0.006 instead of 0.0167.
Where did you get 0.006 here?
Yeah, 0.01 divided by 0.6. Oh, just kidding. I don't know what happened. Never mind.
Okay, so that's right.
Yes.
This is correct. Good. But the natural log is off. Okay. See? Definitely get this wrong on the test if it was me. All right, thank you. All right, let's do it again one more time. Take 2 here. All right, so obviously if you have the correct equation, it's natural log of Q, and Q we calculated here is 0.0167. So natural log of 0.0167, close those parentheses. We get that, okay, now this is tricky, times 0.0257. I'll close those parentheses, divided by 2. But you see I have a minus sign here. So minus into a minus becomes plus. So this becomes minus into a minus is plus a minus, plus into minus is minus, plus a minus 0.04. 0.012, 0.013 volts. Okay, I got confirmation. So let's do 2 sig figs. Yeah, 0.013 volts. Okay, so at standard state, this is non-spontaneous. Standard state, that is. Under these conditions, under these concentrations, it is spontaneous. Under these concentrations of whatever, cadmium and iron, it is spontaneous. So you see, things really change if you play around with the concentrations. Right, are there any issues or problems with this particular problem? And it is a problem. Gave us a problem. Okay, are we good? So just be careful, like just be careful on the test. All right, so what is the EMF? Remember, EMF stands for electromotive force. I have a galvanic cell consisting of cadmium plus 2 cadmium half cell, and this PT stands for platinum. So really, it's not a part of the. You don't really need it in the problem, but platinum is just the solid. H plus is in liquid, and H2 is the gas. So the gas actually sort of forms on the platinum. But you don't really need the platinum to solve this problem. So that's a half cell. So let's just write our half cells here. We have CD plus 2 and CD half cell, and we have an H plus H2 half cell. This is in platinum. If the cadmium is 0.2 molar and H plus is 0.16 molar, and this pressure of oxygen is 0.80 atmospheres, if this reaction were to happen spontaneously. Okay, sorry about the blurriness. Did not see that coming. So once again, you don't need the platinum to answer this. What you need is the H plus H2 half cell, cadmium plus 2 cadmium half cell, and we are told the reaction is going to go. Okay, it's going to move to the product side. Right, so let's write out these individual half reactions. All right, we have here cadmium plus 2 going to cadmium. How many electrons and where? Okay, 2 electrons on the reactant side. Everyone see that? That balances this out. And what is that on our table? We just 0.4? Negative 0.4 is right. Okay, this is a solid. Okay. And then we have H plus going to H2 gas. How many electrons and where? First, let's balance the hydrogens. Okay, don't. Balancing out the hydrogens, and we have a 2E minus here on the reactant side. We have to flip one. So H plus to H2. I think that's 0. You're right. H plus to H2. Everyone see that's a 0? Just looking it up. All right, so which one should we flip to make sure that it is spontaneous? We're going to flip the top one, because remember, they tell us that the reaction is to happen spontaneously, so we need a positive voltage. So let's flip the top half reaction. Flipping the top half reaction, this is what we get. We will get cadmium solid goes to cadmium plus 2 aqueous plus 2E minus. Let's flip that sign to 0.440 volts. Very good. We'll leave the bottom the same. And 2H plus 2E minus, leaving the bottom the same. 0.0 volts. And this is a 2 electron transfer reaction. Everyone see the 2 electrons cancel. And now we have here cadmium solid plus 2H plus goes to cadmium plus 2 plus H2 gas. Okay. All right, let's put our equation here. I'm going to use this side of our notes. Our equation is going to be E equals E cell minus 0.0257 divided by N natural log of Q. Natural log of Q. Okay. So this is the same thing as E cell minus 0.0257, divided by N natural log of products over reactants. So net products is pressure O2 times concentration of CD plus 2 divided by concentration of H plus. We have to square it. So don't forget the square, because we have 2 H pluses, we have to square it. All right, let's plug in our numbers here. Okay, everyone see why I squared H plus? Q is products over reactants. Okay, Q is the same thing as K. We use it to compare to K. Products over reactants. All right, our E cell we just calculated here is 0.40 volts. So 0.40 volts minus 0.0257. How many electrons are being transferred here? How many electrons are being transferred here? 2, right? Everyone agree it's 2? 2 times natural log. The pressure of H2 gas is 0.80. Okay, I'm not going to put units here. I'll put the units at the end. Actually, Q has no units. 0.80 CD plus 2 is 0.20 molar. Divided by H plus squared, 0.16. We have to square it. And that will give us the E of the cell under these concentrations, okay, under these conditions. And let's go ahead and do that. Let's be careful on our calculator as before. So here's how I'll do it. I'll do 0.80 times 0.20 divided by 0.16 squared. Okay, 6.25. Let's natural log that. Equals that number times a minus 0.0257. Divide that by 2. Okay, everyone with me? Plus 0.40. Plus 0.40. And 0.376, 0.38 volts. All right, I don't hear any disagreements, so I'm just going to go with 0.38 volts. Okay, don't forget the units of the E is going to be volts. Volts V. Volt V. Okay, so under standard state conditions, here is the cellular voltage, or the galvanic cell voltage, 0.40. And under these concentrations, it's a little bit lower, 0.38 volts. Okay, under these concentrations. Under these concentrations, it's 0.38 volts. Under standard state, it's 0.40 volts. Okay. All right, so that is that problem. Let's go ahead and do this problem here. Okay. Consider the following cell diagram. So let's not forget that the way this thing works is an anode couple. We put two lines that represents a salt bridge, and then we follow it with a cathode couple. So we have Mg solid going to MgSO4. Here, you're going to have to realize, or you will have to surmise, that SO4 minus 2 is a spectator ion. It's not really involved in this reaction. Okay, what is really happening is Mg solid going to Mg plus 2. Okay, so remember, magnesium sulfate in water, magnesium sulfate in water is nothing more than Mg plus 2, and then the SO4 minus 2 is just an ion in water, not really doing anything. Okay, we call that a spectator ion. All right, so that's our anode couple. Let's balance this. How many electrons and where? 2 electrons on the product side. And what is that on our table here? Okay, it's 2.37 positive. Okay, because remember, it's flipped. It's an oxidation, so positive 2.37 volts. Okay, that is our anode couple. Let's do our cathode couple. And that is nickel sulfate. Well, again, you need to realize that nickel sulfate, hopefully you guys remember your ionic compounds and how they switch. So because SO4 minus is a minus 2 charge, nickel, because of switcheroo in ionic compounds, we switch to charges, the nickel is a plus 2 here. Okay, so nickel sulfate in water is nothing more than nickel ion, nickel plus 2. And sulfate ion, which is a spectator ion, meaning it's there, but it's not really doing any reaction. It's just dissolved. So that's happening in our cathode couple, and let's go ahead and write that half reaction. We have Ni plus 2 going to Ni solid. All right, how many electrons and where? 2 on the reactant side. Very good. And let's see what this looks to be in our... You guys found it? I did. I guess I won that race. We have races. Who can find it first? Is it minus 0.14? It's minus... Wow, that's really bad. Exactly. Okay, minus 0.25. We'll leave it as is. Okay. So anode couple, cathode couple. Realize that nickel sulfate is nothing more than nickel plus 2. Magnesium sulfate is nothing more than magnesium plus 2. The SO4 is a spectator ion. It's just there. All right, we don't need to multiply anything out, so the 2 E's and the 2 electrons cancel. So N equals 2 here. It's a 2 electron transfer reaction. And our net reaction is nickel plus 2 aqueous plus magnesium solid is going to give us Mg plus 2 aqueous plus nickel solid. 2.37 plus a minus 0.25, what is that? 2.12 volts. Okay, 2.12 volts. That's going to equal our E cell. And let's go ahead and use the Nernst equation now, because remember, what is our concentration of Mg plus 2? 0.4. What is our concentration of Ni plus 2? 0.6. Okay, so let's go ahead and use the Nernst equation here, which is this: E equals E cell. Okay, I'll use the log version, just in case anyone... I'll use this version. It's the same thing. E cell, standard state minus 0.0592 divided by 2 natural log, log of Q. Q here is going to be concentration of Mg plus 2, is it not? Products over reactants divided by the concentration of Ni plus 2. All right, E cell, we just calculated that is 2.12 volts minus 0.0592 divided by 2. The log, Mg plus 2, what is its concentration? What is the concentration? Everyone agree it's 0.4. And what is the concentration of nickel plus 2? 0.6. So in our calculator, that's 2/3. 0.4 divided by 0.6 is 2/3. Okay. Log of that number. Negative. Negative times a negative is going to be positive, so times a negative 0.0592. And divide that by 2. And then, so the negative and negative is positive, so plus, this thing has a plus in front of it, plus a 2.12. About 2.12, or actually we'll say 2.13 volts as our answer under non-standard state conditions. All right, in part B, how does the cell voltage change? I don't know if you guys can read this. Okay, how does the cell voltage change when magnesium is decreased by a factor of 4? So if our magnesium decreases by a factor of 4, what is its new concentration? What's 0.4 divided by 4? Okay, new magnesium concentration in part B is 0.1 molar. So what we need to do here is substitute 0.10 molar here, everything else being the same. So let's do that quickly. We'll use our second sheet of paper. So part B. Decreasing magnesium by a factor of 4. Which means the new magnesium concentration is going to be 0.1. Okay, it was originally 0.40 molar. They tell us we decrease it by a factor of 4, so now it's 0.1 molar. And that's it. We just plug everything back in. Let's write down our equation one more time. E equals E cell minus, I'll use the I will use the natural log version this time. In part A, I used the log version. Here, I'll use the natural log version. You'll get the same answer. Whether you use this or this, you will get the same answer. So E is equal to E cell minus 0.0257 divided by N. Natural log Q. Remember, Q is concentration of magnesium ion divided by the concentration of nickel ion. All right, magnesium has gone down by a factor of 4. Nickel stays the same. E cell, which we calculated before, is 2.12 volts. That was our E cell here. Minus 0.0257. This is still a 2-electron transfer reaction. Nothing has changed. Still a 2-electron transfer reaction. Divided by 2, natural log. What has changed is our new magnesium is 0.10 molar. The nickel has stayed the same at 0.60 molar. All right, so 0.1 divided by 0.6 is 0.1666, I believe. Yeah, 0.11667. We'll take the natural log of that minus. So the minus times a minus 0.0257. Okay, this math can get tricky. This minus times a minus 0.0257, it'll be a positive. Don't forget to divide it by 2, and then add 2.12 volts. And we're getting about 2.14, kind of the same thing, 2.143. We'll just call it 2.14 volts. Okay, so at standard state, it was 2.12 volts. Decreasing magnesium by a factor of 4, it's 2.14 volts. So a little bit of an increase in the voltage. All right, so that is it. We are done. So you can all pat yourselves on the back for a job well done. And we will review on Monday. So see you all on Monday. Final thing. Just give me one more minute. Let's do our housekeeping. Turn in homework 18. Turn in your lab notebook. If you turn in your lab notebook Monday, I'll give you 100 points. Okay, hopefully you've done all 6 labs, but you don't have to do the lab on the problem set. All those problems, you don't have to put that in your lab notebook. So really, I'm looking for 5 labs. If you don't turn it in, I mean, it's not going to hurt it may decrease your grade slightly, but if you turn it in, it will definitely help your grade. And then turn in your lab reports on spontaneity. And that problem set's kind of late, so I may have to deduct late points, but I definitely want to turn in that lab report in, as well as the second to last lab. And we'll have a review on Monday. Your test is Wednesday. Have a good weekend, one and all. Be well.